Welcome to another meter test. I got a special meter for you this time. It's a new brand that I've never ran before. Before we get started though, I'd like to talk a little bit about these two meters. Before I started all this testing, I had made comments about never spending anything more than $50 on a meter. This is a Maztec that's sold by Harbor Freight as a part number P98674. This meter is actually better than any meter that I've ever owned up to the point of running these tests. My normal use for a handheld meter, I'll have it outside. It gets used around the cars and they get dirty, they get dropped. So they have a pretty rough life, so I don't like to spend a lot of money on them. But I thought about buying a high-end meter at one point. So I looked into buying a Fluke, and I also looked into Keysight. I had problems with getting those companies to respond to any questions that I had. So I ended up going with this Bryman, which again I've been quite happy with. And since then I've ran several Flukes. I've run the 110, the 107, the 115, the 17B Plus, the 87V, and I've had pretty good luck with them all except for the 87V. So today what we're going to do is run this meter. This is made by Keysight. It's a model 1231A. It's a very low-end meter. Cost on this is about $100. You can do data logging with it. If you want to measure current or temperature, you have to have a separate auxiliary probe. But the reason I want to run this particular meter is I believe it has gas discharge tubes in it. You may remember this prototype board. I showed this in some earlier videos. This has a couple of gas discharge tubes on it and a few MOVs. There's also a couple of diodes in here back to back that I'm using as a clamp. The reason for running this board originally was to show how the gas discharge tubes behave relative to the MOVs. They do switch quite a bit slower, so my concern would be that the components downstream from the front end protection may get damaged because of the speed of the gas discharge tubes. I think before I'd invest in a higher end Keysight meter, I think I'd rather run something like this, just get an idea for how robust their front ends are. So that's what I'm looking to do today. So what I'd like to do is actually take this thing apart. I'm going to trace out part of the front end, and we'll make sure that the front end is actually designed using gas discharge tubes. I'll try to determine some of the values for the components used, and we'll sketch up a little schematic for it. And the first thing we're going to do is have a look inside the box. Just letting you know that they are now called Keysight. We can see the meter is rated for Cat 3600. Pretty typical for the meters I've been testing. Only two connectors. It's kind of like the Fluke 101. Little note. It says here, they highly appreciate my business. It's a pleasure to provide me with some Agilent high quality instruments. It says they look forward to serving me again. You know, again, I bought the Bryman because I couldn't actually get any information out of these guys. Kind of sad. Here we have the certificate of calibration. You can see the date here is May the 7th, 2015. So this particular meter is about 8 months old now. Looks like this is the quick start guide. Pouch with accessories. Leads look very familiar. These probes are marked Cat 4 600 and Cat 3 1000. They're rated for 10 amps. I assume these are all pretty much molded by the same company. Maybe not. You can see the end here is a little bit different. These are of course marked Agilent. Could be a newer mold. They definitely like that two color. So I think before we do too much with it, let's just go ahead and install the batteries. I'm thinking it's a reused case and possibly the circuit board. Hey. Okay. So after going through all of the literature in this box, believe it or not, this is just a safety guideline. And we have this getting started manual. There isn't actually a real manual that's supplied with this unit. Unbelievable. So you have to download the manual for this meter if you want it. If you buy a meter like this, I recommend you do that, because that's going to tell you how to change some of the features of the meter which aren't in the Getting Started guide. As you can see, I've taken the unit apart. One of the things you'll notice is the shield has this area removed. One of the meters I had tested, it actually arced from the input side up to the shield, then down to some of the springs. I would not be surprised if this is not why this area was removed. So it actually sits right over the top of this high voltage area here. This is the voltage input. You can see it connects to the two high voltage resistors up to a couple of PTCs, and here are our gas discharge tubes. Looks like a couple of ferrites up in here. Thing I'm not seeing with this is any kind of secondary protection, so I would expect some kind of clamps, and maybe that's what they're doing down here. I'll have to look, but that would protect the rest of the circuitry downstream. One of the interesting things with this meter is look how complex this is. I would have thought this would have been a lot simpler for the functions that this meter has. See from the board, this board is actually used for multiple meters. Looks like Rev 8. If we look right in this area here, it looks like all of the through-hole parts are hand soldered. I don't know if the camera will pick this up, but there's a lot of flux residue around the PTCs and around the two high voltage resistors. You can really see it from the bottom here. Made in Malaysia, of domestic and foreign components. I'm not real impressed with the switch. You can see this trace right here. That's the common trace that ties the two gas discharge tubes back to the ground reference. So that trace connects to here, so then goes down to our common return. You know, there's going to be quite a bit of current that's going to flow through this, and I would not be surprised to see a trace that size actually get damaged. Yeah, I guess we'll have to go ahead and test it and we'll see. I traced out the front end of the meter, so the voltage input comes in. This goes to the two high voltage resistors. The green banded one is 263 ohms. The red banded one is 1.028K. The green branches off to two PTCs. The first one is RT2. It measures 706 ohms. And it also branches to RT3, which is a 2.4K ohm. RT3 runs to the selector switch. When VC low is selected, it grounds this PTC. So this PTC provides their low impedance path. The red goes to RT1, which is a 943 ohm. This goes to gas discharge tube E1. It also connects to E2, which I believe is some type of a ferrite. E2 then routes to E3 in DC and diode mode. E3 again I believe is an inductor. What's interesting about this is it drives to 5 2 mega ohm resistors in series. That's these components here, and you can see there's a capacitor in parallel with that whole path, and this goes straight on in. This is a CMOS multiplexer chip. and there's absolutely no additional protection on this line. RT2 goes back to gas discharge tube E4. Both of these gas discharge tubes are banded with a brown and a red. I assume that brown-red banding means it's a 1.2K or a 2.1K volt part. The thing when looking at the rest of this meter is I don't see any additional downstream protection. So just looking at the meter, again, the level of complexity, how dense this board is, I don't have a lot of confidence, to be honest, that this is going to survive any of these tests. So let me put it back together and we'll do some type of a functional test on it. Let's go ahead and do a basic checkout of the meter. So let's see here. Let's be looking at resistance. This will be a 0.5 ohm resistor. Looks very good. 1 ohm. Very good. 50 ohms. Pretty good. 100 ohms. 1K. 10K. 100K. 1 meg. 10 meg. Cannot do 100 meg. I think it's limited to 60 meg. Try the diode mode. It's a dead short. Let's read 0 volts. It's a single diode, and these are silicon. 2 of them in series, and 3 of them in series. Let's try the capacitance mode. Let's try a 1 nanofarad. Huh. This would be 100 nanofarad. One microfarad. And a 10 microfarad. It's fairly fast. Now looking at the manual, it can read up to 60 meg, but it can only read up to 10 millifarads. It's a 2200 microfarad 16 volt from Illinois capacitor. You can see sealed. Should have no problem reading this. Let's talk about some of the features of the Keysight. This meter does not have a temperature input. It does not have the ability to read current. It does support an external probe for both of those if you needed those features. Of course, that would be added cost. This meter is true RMS and has a resolution of 6,000 counts. It does have a bar graph, and obviously it has a backlight, but it's basically a no-frills meter. This Maztec, on the other hand, $50, has an ambient temperature along with an external one, has microamps, milliamps, amps, sound meter, capable of measuring lux. This is not a true RMS meter, but if you're looking for something with a lot of features, it is fairly feature rich, fairly inexpensive. If you're looking for something smaller, you have the Fluke 107. Again, fairly inexpensive meter. It's capable of measuring current. Also has capacitance, resistance, diode check. Can measure AC millivolts but not DC. Again, a no frills meter but very robust. I would choose this over the Fluke 101 only in that it has the backlight and the current input. Again, for $50 we have the Amprobe AM510. Again, this is not a true RMS meter, but it does have a microamp and a milliamp range along with amps. It has non-contact voltage. Again, a very robust meter. Also has a flashlight similar to what the Keysight meter has. The rest of the meters that are shown here, we have the Fluke 115, the 17B Plus, the Bryman BM869S, and the Amprobe AM530. Of these, the 17B Plus is the only one that is not a true RMS meter. So 17B Plus, this is a 4,000 count meter. You can see it reads AC and DC microamps, milliamps, amps, capacitance. Also has a millivolt range. This meter can measure temperature. It does not have a bar graph. The cost of this meter is $156 when I purchased it. Mechanically, it's very sound. I actually like the feel of this meter. It's a good size. Next to it, we have the Fluke 115. This meter costs $132. It has 6,000 count resolution like the Keysight. It's a true RMS meter like the Keysight. It can also measure current, which the Keysight cannot. And it has a bar graph display as well. It cannot measure temperature. To the far right, we have the Amprobe AM530. This meter was supplied by 5KY. This meter costs about $80. It's a 4,000 count meter. It is true RMS. You can see it has a microamp, a milliamp, and an amp range. It has a temperature input. It has non-contact voltage detection. Again, a lot of features. The downside with this meter is it's not very robust. So this meter actually failed fairly early on in the tests. It has since been repaired and recalibrated. And of course the meter that I'm normally using now, this is the BM869S. Again, very feature rich. Cost on this meter is about $230. Definitely in a class by itself compared to the rest of these meters. But not very expensive for what I would consider for a meter with these types of features. Battery life on this meter is very exceptional. It's supplied with a single 9-volt transistor battery. It still has the original battery in it, and it's now been in operation about 5 months. So yeah, I'm very happy with battery life. This meter overall, very good. All 6 meters are currently connected in parallel. These are all attached to my Fluke reference, and it's currently set for 10 volts. We could see the Fluke 115 and the Bryman are definitely reading very close here. So with a 1 volt signal applied, put the Bryman into the 500,000 count mode. We can see it's putting out about 995, 96 microvolts. The Amprobe AM530 is putting out 1 millivolt. 0.9 millivolts for the Keysight. The Fluke 115 is at a millivolt, and the 17B Plus is at a millivolt. This is looking at a half a volt applied. This is looking with a 5 volt signal. Again, this is a sinusoid. Currently the generator is set at 100 Hertz. This will be 101 Hertz. This will be 123 Hertz. It's 200 Hertz. 400. But that Keysight is really slow. Let's go to 800. You can just see how long this thing takes. Here's 1 kilohertz. Two kilohertz. 4 kilohertz. 8 kilohertz. 10 kilohertz. 20K, 40K, 80K, 100K. See, the Fluke 115 is starting to drop out. 200K, 400K, and we can see the Keysight now has dropped out. This is currently with a 1 second sine wave applied. Again, the Fluke, the Keysight, and the amp probe are all set to manual range. The Bryman is currently set to auto range. This is with a 2 Hz signal. This is a 4 Hz signal. Here's with a 10 Hz signal. Here we are with a 20 Hz signal. Always impressed me with the Bryman is that you pretty much see the bar graph using the entire scale, which is what you'd expect. The rest of these, it's like they do some kind of averaging and they'll filter it down. Here's looking at the backlight for the 5. And here we're looking at a rectified AC signal. Again, the Bryman is the only one that supports the AC plus DC. This will give you an idea of the loudness of each of the meter's sounders. This is the 17B plus. This is the 115. The U1231A. The AM530. And the BM869S. This is looking at a plus or minus 3 volt pulse waveform. So basically it's at 3 volts for 0.1 second, and the rest of the time it remains at minus 3 volts. You can see the Bryman picks up the minus 3 and the plus 3. You can see our amp probe AM530. The minimum is 2.992 volts. The Keysight meter reads 2.412 and 3.02. The Fluke 115 is reading 2.43 and 3.025. And the Fluke 17B Plus is reading negative 3.01 and 1.588. So the 5 meters, the Bryman is the only one that displays this information correctly. This probe is currently connected to an RF generator, and I'm putting out about 500 megahertz. You can see this amp probe is really affected by this. See the Fluke 115? This is at roughly 280 megahertz. It's reading 997, 999, 997. Nothing as bad as the amp probe. Check this out on the 115. 8.9 versus 1.0. See the Keysight meter, same thing. 988. I didn't really see any other frequencies where they're sensitive at. Okay, for the first test we're going to look at the continuity. Well, you can hear how scratchy that is. It's fast, but very scratchy. So non-latch type. So the first thing we're going to do is look at the open circuit voltage. Again, I'm just using my HP bench meter to make this measurement. And next we'll measure the short circuit current. Again, we're going to be using our resistive decade box. And we're going to measure the resistance where it detects the short at. That's pretty crazy. This thing's only got like 1 ohm of hysteresis. This is fairly low resistance it requires. And again, we're going to look at the upper frequency that this can handle. This is 20 hertz. Again, this is a 50% duty cycle. It's interesting, it's kind of like training. I was looking at the manual for the U1231A, and they specify this for a maximum of 600 volts. So that looks pretty good. Definitely can withstand what they rate it for. 653 volts. Oh, there it goes, overload. Right. Just a little over 650 volts, it'll overload. Next we're going to apply our ESD test using the piezo grill igniter. Okay, we'll go ahead and functional test. Okay, all the basic functions seem to work. Next we're going to attach our transient generator. And we're going to supply our 220 volt rectified AC signal. So I'm applying a 0.5 ohm resistor right now. The meter has not been nulled. Okay, we're going to enable the 220 volts because it appeared to take quite a while to recover after this test. And I'm assuming that's because the PTC is heated up. And you can see here it's reading a negative resistance. So I'm putting this on a 1 ohm resistor. Let's just see how long it takes to recover. I wanted to understand why when you apply AC in the ohms mode it causes such an offset error. As it turns out, RT2, which is this one here, and RT1, which is this one here, both get extremely hot when it's in ohms mode and you have the AC voltage applied. If we look, for example, at this node, it routes through E2 and it works its way up to these diodes in this area. The same for the second gas discharge tube. It also routes to the diodes in this area. And when you select the ohms mode, it basically enables these diodes, which clamps the voltage at these two locations. And you'll end up getting about maybe 5 volts here. So the entire voltage drop is across these two resistors in the PTC. And it basically holds the side of the gas discharge tubes, not at ground, but a few volts above ground. So all that power gets dissipated by these two devices. So there is some downstream protection for ohms mode. Again, these are not in play when it's in voltage mode. So again, I think it's just going to be interesting when I finally do test this thing on the transient generator